Hello everyone, I am Subhash from 4th year EC department, NIT Andhra Pradesh. In this video, we are going to talk about relational descriptors. Descriptors. In image processing, visual descriptors or image descriptors are the descriptions of the visual features of the contents in images, videos, or algorithms or applications that produce such descriptions. They describe elementary characteristics such as the shape, the color, the texture, or the motion. Relational descriptors. Relational descriptors are used to rewrite rules for describing the structure. By using these descriptors, we expand the concept of texture. The purpose of these descriptors is to rewrite rules for basic repetitive patterns in a boundary or region of an image. Here, we can consider the example in the figure shown beside. We assume that image is the segmented part of another image and we need to code it in some formal way. So we define the two primitive elements such as A and B and we code it to get the figure shown beside. Here A represents the rightward direction and B represents the downward direction. Now let's talk about some rewritten rules. The property of the structure is the repetitiveness of these elements A and B, which are the constants. Here a simple description method is to formulate a recursive relationship involving the primitive elements. One such method is to rewrite the rules. The first rule is capital S should be replaced with small a and capital A. The second rule is capital A should be replaced with small b and capital S. The third and final rule is capital A should be replaced with small b, where capital A and capital S are the variables and the elements A and B are the constants which corresponds to the primitives which we just defined. Here, rule 1 tells that the starting symbol capital S can be replaced by primitive element small a and the variable capital A. This variable capital A can be replaced by small b capital S or by small b alone. Replacing with small b capital S will move back to the initial rule and the procedure will be repeated. Replacing a by small b alone ceases the procedure. This is because no other variables are remained in the expression. From figure 3, we can understand some sample derivations of the mentioned rules. Here, numbers below the structures represent the order in which the first, second and third rules were applied. These rules will always force A to be followed by B. That is why the relationship between A and B is always preserved. In this way, by using these three rewriting rules, we can generate infinite similar structures. For example, if we consider the first image, the A and B were written using the first and third rules, but this is not the case in second and third images. In the second and third images, the initial B's were written using the second rule, but the final B's were written using the third rule. Why is that? Because if we are terminating the segment of the image using B, then that means we are using the third rule. But if that's not the case, it means we are using the second rule. Now, let's talk about the string representation. Strings are one-dimensional in nature. To use these strings for describing the image, we need to establish an appropriate technique to reduce the two-dimensional position relations to one-dimensional form. Most of the applications of these strings to image description are based on the idea of extracting the connected line segments from the objects of interest. One approach is to follow the contour of an object and code the result with segments of specified direction and length. We can see this from the side image. Another approach, which is more general, is to describe the sections of an image by directed line segments which will be joined in other ways besides head to tail connections. We can see that from the first image. In the second figure, we can see various typical operations that can be performed on these primitives such as a or b, a minus b, a into b, etc. The figure on the left side shows a set of specific primitives consisting of line segments which are defined in four directions. The figure on the right side shows the step-by-step generation of a specific shape where tilde represents the reversed version of that particular primitive. Here, in the second image, we can see various mathematical operations performed on the image segments. Some of them are C plus negation D plus C plus negation D, A plus B into C, and etc. Here, T represents the tail of the segment and H represents the head of the segment. Till now, we have learned a lot about relational descriptors. Now, let's try to execute the same using Matlab. In the first line, img is equal to image read of dip.jpg. We are reading an image with the name dip.jpg. In the second line, we are displaying the image using IAMShow function. In the next line, we are using IAMBinaries method to convert the image into a binary array. In the next line, IAM underscore bin is equal to 1 minus IAM underscore bin. Here, we are interchanging the black and white parts of the image. Here, in the next line of the code, we are using bwBoundaries function. This particular function will create the boundaries for 6 white parts of the image. In the next line, we are using bw of 1. This particular function will save the first white part in b underscore variable. In the obtained image, we will have a lot of samples. So, by using the while loop, we are decreasing the sample count by 10. And then, we are using the plot function to plot the same image. The output of the MATLAB is shown on the screen. In the next part of the MATLAB code, we are defining a variable called ANG. In this variable, we are saving the slope angles of all the 2 consecutive points of the previous variable array small b. After that, we are creating another variable called angle2. In this variable, we are mapping the angles which are present in the angle variable to 0, 1, 2, 3, 4, 5 and 6 and 7, where 0 to 7 corresponds to A, B, C, D, E, F, G and H. The output of angle 2 can be seen on the right side of the slide. In this part of the MATLAB code, we are mapping E, F, G, H to negation A, negation B, negation C and negation D by using several if-else conditions. We are creating RES variable and appending the values to it based on the if-else conditions. After the loop is fully ran, we are displaying the output of RES variable. This RES variable is the string approach we have discussed earlier. In this part of the code, we defined a variable small l to store the length of the line segment. After that, by using the for loop, we joined all the different points. Here, we started from origin 0, 0. In the last 2 lines of the code, we joined the last point with the first point. After this, we plotted the variable. The output of the plot variable outputs an image. This particular image looks similar to the image which we got using bwBoundaries function. This is the MATLAB execution of relational descriptors. Hope you have liked it. Thank you for watching.